Advanced Algebra, Function and Graphical Reasoning, Standard 3.1. A one-to-one function is a function where every output has exactly one input. No horizontal line can cross the graph more than once. Now, a function is the opposite, where every input has exactly one output. But if you can say both that and the reverse, as you read here, then it's a one-to-one function. So let's illustrate that. The following is not a function at all because you have one input that matches two different outputs. This is a function, but not one-to-one. If you notice on the left here, every input has one output. However, there's an output which shares two different inputs. Okay, so it's a function, but it's not one-to-one. This illustration is a one-to-one function because every number on both sides has exactly one partner. There's no shared partners on either side. Sometimes you have to restrict the domain to have an inverse. So restricted domain are the x values that are allowed for a certain function. This involves purposefully not allowing some x values that otherwise work mathematically, but would make the inverse of that function not be a function. So that's a lot to process. Let's look at an example. Okay, so let's find the inverse of f of x equal to x squared. Now finding the inverse again, change f of x to y, switch x and y, and then solve for y. So if you'll notice, the inverse is the square root of x. And it is true mathematically that this function needs to have x values that are non-negative. Like for example, you can't take the square root of -1 among real numbers. However, if you look back at the original function, it would have been perfectly fine to have negative values. But in order to have the inverse, we have to restrict those negative values, or else there wouldn't be an inverse. So to see that graphically, here's the function f of x equals x squared. We talked about the graphs. So if you fold it along the line y equals x, notice the green graph looks like the reflection. However, the green graph is not a function because a vertical line would touch it twice. That leads back to the red graph, the original function, which is not one-to-one because a horizontal line would touch it more than once. So our solution to that is to chop off the negative numbers so that now the function is one-to-one. And when you reflect it, the green function now does not violate the vertical line test. Okay, so you're going to see that restriction of a domain so that a function now can have an inverse. The second part of the standard says to limit the domain of inverses where necessary to maintain functionality. Okay, we want the inverse to actually be a function, so it must pass the vertical line test. The composition of two functions, or two inverses rather, is x. Okay, so if you take f of f inverse of x, that should be x. Here's a sixth example. Verify that f of x equals 2x plus 6 and g of x equals 1/2 x minus 3 are inverses. Now one way to do that would simply be to start with one and take its inverse to see that it's the other. But you could also take the composition. Remember from earlier that the composition of two functions is essentially putting one function into the other. So color coding here, if I put the green function g of x into f, the green function takes over for x. This original yellow x is gone, and instead you have the entirety of the green function. We then distribute. 2 times 1/2 x is just x, 2 times -3 is 6, and then -6 plus 6 is 0. So therefore, we have f of g of x is equal to x. Now that verifies that these functions are inverses because you get exactly x for the composition. A seventh example is asking the same thing. Notice here that though you are allowed mathematically to have, say, 0, for example, be put into this function, we restrict the domain so that the inverse right here is okay. Okay, so I put the square root of 1 into that position. And again, you see why it's x. FGR.3.1 third part says prove by composition or verify by inspection that one function is the inverse of another.